All right. Where we left off last time, I wanted to take a little time to go back over it again briefly because it looks so much like the rest of the standing wave stuff we're going to talk about. So we're going to go very quickly over standing waves on a string, and then we'll talk about standing waves and types in other geometries, let's say. Because some of this stuff also applies to other things. So we'll talk about that a little bit. But in general, the way it's always going to be phrased to you is a pipe or an instrument or a string is going to have, a wave propagate along it. And the gist of what happens is the wave reflects. If it reflects off a fixed end, it flips over. If it reflects off a free end, then it doesn't flip over. But either way, it's going to interfere with itself. The reflected wave interferes with the wave that's continuing to move towards the reflection. And so for certain frequencies, you get resonance. You get that a wave builds, a standing wave forms that will show we'll at least try to image it later in the slides. But the gist that we have here is for a stringed instrument, normally we can find the velocity based on the properties of the string, based on the mass of the string, the length, and the tension in the string. All right, so that's important to remember. And it also goes with frequency and wavelength because that's a definition. But the gist that we have here is that when we form these standing waves, they form patterns. They form fairly obvious patterns between two fixed points. The fixed points, the points that don't change, that have an amplitude equal to 0, are going to be called nodes. And what I'm going to do is go ahead and mark in the slides again. These points that are stationary are nodes. And then also the endpoints. The points that are large amplitude are antinodes. So in this bottom row, we'd have an antinode there, and there, and there. And then we'd have one there, and there. And then on the first row, we'd have one there. And so you can see the kind of pattern that you get. And for a fixed string, the antinodes, how many antinodes there are, tells you what harmonic it is, or tells you, basically tells you what n is for a stringed instrument. Whether it's worth it to learn that as a rule of thumb is kind of weird because we're going to get into stuff where it doesn't apply, but for strings, it works. So we identify the nodes, identify a formula for the frequency. The frequency is based on the speed and the wavelength. But the wavelength has to be a function of the length of the string. It has to fit on the string in some way. You have to put a half wavelength or a whole wavelength or multiples of a half wavelength on the string. So we can identify the frequency and the wavelength. And a cleaner way of expressing it is this formula where the nth frequency that fits on the string is n times the velocity divided by twice the length. The assumption is you have to have at minimum half a wavelength to fit because that's the distance between two nodes. And you have two nodes because they're the fixed points on the string. So you go up from there. So you can go from one half wavelength to two half wavelengths to three and so on. And so you can also make this nice statement that if you know the fundamental frequency, the nth frequency is just n times that. Now, if you're doing this in a music background, it might be a little bit unintuitive. You would think, well, the next harmonic would be like an octave up. And then the next note, well, that's not an octave up, it's like a fifth up. Because it really is doing numbers on, it's fitting waves to the string, or it's fitting waves to the pipe. But the important bit is these formulas that we have. And there is another formula that I want to put in here. And that is, if you know two harmonics that are next to each other, or if you know like the third and the fourth, then you can write the fundamental frequency is the nth one minus the n minus 1. All right, so the fourth minus the third would give you the fundamental. And that's a thing that comes up in some problems, is because of the way the ear works, right? The ear's range of hearing is from 20 hertz to 20,000 hertz or so. And of course, that depends on your age and the structure of your ear. You know, there'll be, you know, if you're old, like I will be, hopefully, then, you know, your hearing goes. And it goes from the high end. Anyway, the point of this is there are sounds that you could possibly not hear. All right, if you set up a guitar string that could play at 5 hertz, you wouldn't be able to hear it. But you'd hear the fourth harmonic because it'd be at 20 hertz. So you just barely hear it. So we talk about guitar. You know, the idea is changing the length changes the natural frequency. Right, so that's, you know, the frequency absolutely depends on the length. So we worked through a problem where we specified exactly what mode of standing wave was on the so I should be careful, go back here. When we talk about these patterns, which harmonic, right? When we say n equals 1, that is the first, you know, the first mode, or sorry, the n equals 1 mode, and then n equals 2 mode. So you may see that terminology. So we worked through a problem where, you know, it was given a frequency and the length of a string and the mass of the string. And we're told what mode it was operating in, which gave us an idea of what the wave looked like. And so I drew it here in blue and red. And so we could deduce the wavelength had to be 2/3 of the total length. All right, because the formula is lambda is 2L over n, and n was 3. So we knew it was 80 centimeters, and we deduced the velocity from frequency and wavelength. And then we deduced the properties of the string to get to the tension. All right, so we worked through it in a couple of different ways, but and then we talked about this problem. When there's a any standing wave, the idea is from node to antinode has to be a quarter wavelength, and from node to node or antinode to antinode has to be a half wavelength. Because that's the definition of what a cycle of a wave looks like. Right? A wavelength has to be from crest to crest or trough to trough, or from one node to another node where the velocity is in the same direction. So this distance is a wavelength, and so you can label these. There's a node, an antinode, a node, an antinode, and another node. And so to the nearest antinode is a quarter wavelength, to the nearest node is a half wavelength. And we select the correct answer. So this is where we're going to get into, like the example we gave with the string is a transverse wave. The string obviously moves side to side, not along its length. But there's no reason why you couldn't set up standing waves in a longitudinal medium, like sound. And so that's what we get into with sound. Now, for sound, we've got a couple options. Usually with a string, we can't just have a string that's free at both ends or free at one end. It just kind of doesn't do that. You know, you need tension in it, and to put tension in it, you need two fixed ends. Sound does not have that. So we got two cases we can care about. The case where both ends are closed doesn't matter because you can't vibrate the air inside. But a case where both ends are open. So this is all of the flute family. And maybe there's some other instruments, but I'm not for certain. All of the flute instruments are essentially a pipe with two open ends. And so the way you would think about this is those open ends, there's nothing restricting the movement of air. So the amplitude absolutely can change. So they must be antinodes at each end. And then the formula is going to again be lambda is 2L over N. You're going to have the same formula. So for the first harmonic, the length is going to be half a wavelength. And the half a wavelength has to go from antinode to antinode. So it has this pattern where you have a node in the middle and another antinode. All right, so going back to, I said node and antinode a lot. The ends are where you can have the pressure change a lot. The antinodes, the sound pressure changes a lot. There's a lot of motion of the medium. The nodes are the places where the medium is relatively stationary. The change in pressure in the sound, in the medium, is going to be about 0 at the nodes. So you go through for the second harmonic, there has to be a wavelength, and you can see that wavelength fits from crest to crest or trough to trough. And so the pattern you get looks like alternating nodes and antinodes, and so there's 3 antinodes. And so you'll notice another thing is that the mode is the number of nodes. Right? The n equals 3 mode, there's going to be 3 nodes. This is sort of the mirror image of the string. In the string, both ends were fixed. Here, both ends are free to move. But the gist of this is going to be that we have a formula. And the formula doesn't really care whether we have nodes or antinodes. It just requires the velocity and the wavelength. And we know what the wavelength looks like. It looks like this. So wavelength only depends on the length of the instrument here. It only depends on the length of the pipe. And then the frequency depends on the speed of sound. So speed of sound depends on the material, but we'll generally just give you that, or we'll ask you to calculate. We'll say it's 343 meters per second, unless otherwise stated or otherwise asked for. So, but you can calculate that. Next week will be more of how do you deal with gases and how do you, so we talked a little bit about the speed of sound and gases, but not worrying too much about that. So the gist of it, all right, now the other thing is how do you drive the air? Well, generally you have something, right? If you're playing an instrument, like if you're playing a flute, you're blowing air across one opening. You're pushing air across the opening, and you're alternating how you change the pressure across that opening. And so, if you drive it here in the picture, we're driving it with a tuning fork. You get something kind of looks weird, but ultimately this is a weird graph where you have position on the y-axis and you have change in pressure on the x-axis. It's drawn sideways. All right, that I don't want to keep in the notes. I'm going to erase that. So the gist of it is, for a tube open at both ends, you get the same formula. So that's not what I wanted. That's bad. Why am I doing this? The gist of it is tube at both ends, you get the same formula. And note we specify n equals 1, 2, 3, or 4. In both cases, it just has to be an integer. An integer means you have a half wavelength that will fit in the medium, or multiple half wavelengths that will fit in the medium. All right, so an example we have is playing a flute. So I don't know if anyone's ever played a flute. I've never been good at it. I always lean towards tuba. Though I started clarinet, that was weird. Truth of the matter is I could only play stuff until it broke. Oh, shit. Excuse me. My nose has been running, and that's a bad thing to have a mask on when your nose is running, I think. So, if you've seen a flute, you have an idea about how long it is. It's about this long. It's from, from your face out to about as far as you can reach. It's really a little shorter than that, probably. We'll figure it out. But the idea is we know the lowest note it can play. Right? This is our frequency, and we know the speed of sound. So in principle, we can deduce the wavelength, and so we can deduce the length of the tube. And so the idea is that we model the flute as just a tube. It's the lowest possible note it can sound, which means it's going to be the n equals 1 mode, which looks horrible when I drew it like that. But, a pipe at both ends. And so this distance is lambda over 2 as our length. So we find the wavelength, and then we find lambda over 2. And so the wavelength's easy. We have velocity is frequency times wavelength. So wavelength is velocity divided by frequency. And then from this thing, we have the length is 2 times the velocity over the frequency. No, that's not right. Velocity over twice the frequency. All right, and we have our new fancy formula. The frequency is NB over 2L. So we rearrange this. L is NB over 2F, and N is 1. All right. So in the next slide, we go through the calculation. N is 1. The velocity we know. The frequency we know. F1 is the low C is the 261.6. And we have a factor of 2 there. And right, we have meters per second, and we have hertz is really 1 per second. So the per seconds cancel, we're left with meters, and we get about 65 centimeters, which is about 2 foot. Right? If it's about 30 centimeters to the foot, a flute's about 2 foot long, which is maybe a little high, but believable. It's not 12 foot long. It's not coiled on itself like a tuba. But it's not, it's not maybe the image we have in our head. 2 foot seems okay. So do y'all have any questions thus far? Does that make sense to? Can the Zoom call hear me? I should have gotten a little pop-up that said, no, you can't hear me, but okay. So every other wind instrument is effectively a closed pipe. It's got a closing on one end. And so you can think a clarinet is, there's no way I can draw this effectively. A clarinet is basically a pipe with a opening kind of sideways and a reed. And the reed moves back and forth and flaps. And that that flapping opens and closes it temporarily. But when you're treating it like an instrument, when treated like a pipe, that reed end is closed. For brass instruments, trumpet, trombone, tuba, and the various horns in between, your lips fit into one end of the pipe and they work as that reed. And so you're effectively driving the air from that point, but the air pressure is basically fixed. It's what you're putting there. And the opening is basically closed. So we know at these points where it's closed, these ends all have to be nodes. And we know that the open ends of the pipe, they have to be antinodes. Everything else in between has to be construction that allows us to put a node at the closed end and an antinode at the open. So that changes what frequencies we can have. So we drew n equals 1 in here. Now below this, I'm going to draw n equals 2 or tritone. We have a pipe. N equals 2 would have to look like effectively this. Because that would be effectively this. You know, this is a quarter wavelength. The next one would have to be, but this would be a node here and a node there, and it doesn't work. And an antinode in the middle. It just doesn't fit. So we can't have n equals 2. And the same argument will give us for n equals 4 and n equals 6. Effectively, closed pipes are limited to the odd harmonics. And that's what we have pictured here. The modes are 1, 3, and 5 here. And so we have a new formula. The nth harmonic is n times the velocity divided by 4 times the length. And so what it looks like is we've taken an open pipe and somewhere in the middle where there's a node, we've stuck a thing to close it. We've cut the pipe in half. And so we have a formula for the wavelength. It again only depends on the length of the instrument, and it's 4L divided by the mode. And so we have a slightly, this is not open, it is closed. The original source of these kind of screws it up sometimes. But this is the general formula, and note that n is odd. N must be odd. And then there's some extra links. I don't know if those links work because a lot of them depended on Flash, and Flash is dead, so you can try them on your own. The common sort of example that we have, which seems like it's always on TV, if you've ever watched the Andy Griffith Show. I don't know who watches TV anymore, but they would have the hillbillies come down from the mountains and they'd always have the jug. And they go, boo, boo, blowing across the jug. That's the classic closed. Oh, I actually have a jug. I'll stay back here, obviously, because, you know. But you can hear the tone that kind of forms. By drinking a little bit, I've changed the effective length. It's the effective length, the liquid's not moving, it's the air. So the length is from the liquid to the surface. It's a slightly lower tone. Now to drink, slightly lower. easier to do it if it's the example that we have here, a soft drink bottle or a moonshine jug, which is not really a thing anymore. They go to like milk jugs and canning jars. And those weird 5-gallon jugs with the lid that you can like get gas and kerosene in, but they're like not red and blue. It's weird. Anyway. So soft drink bottle. It's about 15 centimeters tall. All right, that's 6 inches. You blow across the top of it and the bottle's empty. So this represents the length of the pipe. And so we can ask, what is the frequency that's generated? So this is one of those problems where there's a little bit of information left out. So there's a couple different ways to work it. But we are asking for the fundamental. So on the right, we can say, well, the fundamental frequency is going to be 1 times the velocity over 4L. All right. Now on the left, we say, well, what is the wavelength? Wavelength is 4 times the length, and it is 4L over 1. And then related to the velocity and the frequency. So you could relate it in 2 different ways. Easiest way is just to do what's on the right. And the problem we have is we don't know the velocity. So we'll just use a standard assumption, is that the velocity is 343 meters per second. If we give you this on a homework, the homework problem will tell you to assume some velocity. And on an exam, there'll be a statement at the beginning with constants that says, the speed of sound is this value unless we tell you otherwise in the problem. Because obviously the speed of sound changes. So today it's probably like 335 outside, and it's 340 or to 343 in here, depending on the temperature. So what we have here is we have 343 meters per second divided by 4 times 0.15 meters. The meters will cancel, we'll be left with 1 per second, which is hertz. So that's good. We have 343 divided by 0.6. So it's going to be in the range of 570 or 680. And it ends up being 570. Did everyone get that? And does anyone have any questions about this so far? There's a whole lot of, here's a pipe that just happens, here's something that just happens to resemble the instrument we want to talk about. If you cause a standing wave to form, what's its frequency or what's its wavelength? Okay, so another example we have here. I'm going to let y'all work on this for a minute because it's a little tube open on one end, closed on the other. We know the fundamental frequency. You can ask what the length of the pipe is between the open and the closed end. And we can sketch what it looks, what the n equals 5 mode looks like, and ask what the 5th harmonic is. Now, so while y'all are working on the calculation, I want to actually do the sketch. So there's our closed end, and there's our open end. We have to have an antinode at one end, a node at one end, at the closed end. And since it's n equals 5, we know that this length, L, represents 5 over 4 lambda. So we need to sketch in a wavelength and then an extra quarter wavelength. There's our wavelength, and then there's our quarter. and then in blue. So there's our 5/4 of a wave. So again, we're going to do the same sort of calculation. F1 is V over 4L, and N is 1 here. So 343 meters per second. Ooh, that went poorly. Sorry about that. So rearranging this, we would get length L is V over 4F. So 343 meters per second over 4 times 16.4 hertz. So the hertz and the per second cancel out. You get meters. This is 343 divided by about 65. This is where you put it into a calculator. I'm going to find out who's bugging me on the email. And what I get is that L here is 5.3 meters, 5.228. So 5.2 meters. Let's correct that. So the other part of the question, what is the frequency of the N equals 5 mode? That's fairly easy. F5 is 5 times F1. Or you can calculate it from F5. Come on. No. 5 is 5 times the velocity over 4 times the length, which I've written poorly again. So F5 is 5 times the velocity over 4 times the length. So 5 times 16.4, 5 times 16 is 80, so 82 hertz. It's a little bit messy here, but does that make sense to people? Can everyone read it? Does everyone understand it? There's a lot to put on the slide. This is a weird one. We have one pipe, and we're comparing it to another pipe. And this is one of those things where we're told not to assume the speed of sound, which kind of doesn't matter. All right, the point is, the formulas for each of them use the speed of sound. They're going to use the same speed of sound, it's the same air. So we have one pipe that's 78 centimeters long. And we're told that the fundamental frequency in this closed pipe I'm going to draw with some length x. So its fundamental is this quarter wavelength drawn. It's going to equal the third harmonic of the open pipe. So we draw a third harmonic. So that's going to be 1/2 wavelength, 2 halves, 3 halves. So it looks like that. So the wavelength there, right? We have, this is n equals 3, this is n equals 1, that's closed. So the gist of this is we go through and say, well, what do we have formulas that fit these numbers? And so we want to relate to frequencies. That's kind of the important bit. So F3 in the open pipe is 3 times the velocity over twice the length of the open pipe. But that equals F1 of the closed pipe, which is the velocity over 4 times the length of the closed pipe. And so here, now we cancel out the velocities because we have it on both sides of an equal sign. So let's go yoink, yoink. And now we have an expression that relates the lengths of the pipes. We want to know the closed pipe length. The closed pipe, we're going to pull that 4 up here. And that's going to be, right. We're going to flip this over. 4 times the closed pipe equals 2 times open pipe divided by 3. And so we divide by 4. And so the closed pipe is essentially the open pipe length divided by 6. So 78 divided by 6 is 13 centimeters. I realize this is one of these things that I'm sure the teachers have been doing from the beginning of 111 is the goal is not to work with the numbers till you have to. Is to work with the equations, fiddle with those first, and get a generic solution and then plug in the right numbers. So that does kind of leave some of these problems less followable. Does it make sense to everyone that's paying attention here? Good, I hope. All right, so I do want to do one more example. Let me back out of some of this. I have a little time, that's good. Yeah, keep from that point. I want to do another slide. And open. So I want to do an example where start from this slide. All right. So I want to do an example where what we're doing is looking at adjacent frequencies that you don't know what the fundamental is. So the example that comes up in tests and stuff that seems reasonable. You're walking one day and you walk by a culvert in the road. It's a big open pipe on both ends. All right, so one part, go the other way. Turn on the pin. So one part of it is something that looks like this, and some frequency you hear is 56 hertz. And then another frequency you hear is 70 hertz. So we kind of have a question as to what the length of this culvert happens to be. And so the trick is, we know these aren't the fundamental frequencies. because you can tell that one is not immediately a multiple of the other, but they share some sort of common factor in it. And so we're looking at this. When it's adjacent frequencies, what we're going to do is say the first frequency, the fundamental, is Fn minus Fn minus 1, which is 70 hertz minus 56 hertz, which is 14 hertz. So that means we go back and we can identify that what we had here was really, this is the n equals 5, the 70 hertz, and n equals 4 is the 56 hertz. And so the fundamental would be 14 hertz, probably feelable more than it is hearable. But just by identifying from two tones, you can identify the fundamental frequency. And then you can go through and say F1 is 1 times the velocity over twice the length. You know it's open because it's described as a culvert. You can see through it. And so you can get the length is 343 meters a second over twice 14 hertz. So it's going to be 343 divided by 28. Which is 12.25 meters. And that seems reasonable for, a culvert would be a big pipe under a road. It seems reasonable. It's not an outlandish size or a, not describing a big pipe that is a tiny flute. Anyway. All right, so the remaining time, I've got about half an hour if I need it. The remaining time, we're going to start on talking about Doppler effect. If you've ever sat in a car and you've heard another car go by you, you've heard it. As it approaches you, the pitch of the sound picks up a little bit and then it goes down. I'm hoping this video actually works when I click on it. No, it didn't work. So, this is a fire truck going by. And you can hear as it approached, it was a higher pitch, and as it left, it was a lower pitch. So what's happening is you have a source, and it's emitting sound. In this case, this fire truck siren. And as it approaches you, so what's happening is a speaker somewhere or a siren. A siren is a big rotor that turns, and it basically pushes air out of another stator. So it alternately pushes and pulls like a speaker. So speaker pushes and pulls on the air. And so it pushes once when the truck is in one distance away from you, and then the next time it pushes, it's closer to you. And so the effect that it has is as you see the thing approach, the wavelength appears compressed. Right? The speaker is shaking at a particular frequency. And that's when we started this. When we defined frequency, I said the frequency was the fundamental thing to understand. This is the thing that you're counting. So the frequency should, the frequency of the thing shaking, of the speaker shaking back and forth, of the siren turning, that frequency doesn't change. But what you experience, what you hear does, because the wavelength changes. Right, so the Doppler effect here, the story goes, there was a fairly well-off guy. His name was Christian Doppler. And in about the 1860s, he noticed this Doppler effect. He couldn't pinpoint exactly what it was. And he had the idea of putting an orchestra on a train, having the train ride by the station while it was tuning. And he could hear its tuning pitch go up and back down. Of course, it might have been reversed. It might have been at the station. He might have been on the train. But just as fundamentally, it doesn't matter whether the source is moving or whether the observer is moving. The effect is that you will get this compression or this stretching. All right. As the truck goes by, the speaker will shake in one position, and the next time it pushes air towards the observer, it's further away, so it appears to stretch it. So the Doppler effect is that change in pitch, that change in frequency that you hear, not to change in the source, the change in what the observer sees, based on the fact that there is a relative velocity between the source or the observer and the air that's moving through. So that's another important bit, is it does matter what thing is moving, right? Because you'll get slightly different answers if you assume that the observer is moving or if the source is moving. And the reason it is that they each have a velocity relative to the air. And the assumption is the air is stationary. This gets simpler when we talk about light because there's no assumption of air. It just matters how fast there is motion between observer and source. But here, when it's sound, it's more complicated. It's the motion of the observer and the source relative to the medium. So when we talk about the formulas, this is the important bit. It's velocities relative to the medium. So a lot of this is derivation. You don't need to copy the derivation down. It's just justifying what's going on. All right, if the source were at rest, it would put out wave fronts, or it would put out a compression with a distance lambda, the wavelength between compressions. But as the truck moves, it covers some distance, velocity times time, based on the velocity of the source, or the velocity of the truck. And so it appears as if the wave fronts are closer together, some distance lambda prime. And we can calculate what that is, and then we can calculate the observed frequency based on this new wavelength and the velocity. But the new wavelength is just a function of the sound, the speed of sound and the source frequency. And so we get this formula that looks like this. Now, before you write down formulas, I'm going to go to eventually a very generic formula. That will be one formula that covers everything. So I just want to be clear about that. And of course, note, this is saying towards the observer. So if you're moving away, the derivation looks similar, except what's happening is instead of taking off this little chunk of distance, you're adding a chunk of distance on. And so in these formulas, instead of having minus signs, you have plus signs. And so you have something that looks like this for a stationary observer. Now, we can ask, well, what happens if the observer is not stationary? Right. Well, first, we can go through an example problem. Actually, let's skip that. We'll come back to it. So, if the observer moves, then what's going on is, as the observer moves, they experience the wave fronts faster than they would if they were stationary. And so the observed frequency looks like the source frequency plus a correction term because they're moving faster. And so you end up with something that looks like this. And so moving towards the stationary source, it looks like these formulas. And again, if you're walking away from the source, you get a minus sign instead of a plus sign. So we're going to skip these for a moment. This is the general case because it covers all the possibilities. Both observer and source can be moving. And it uses these symbols. Who has seen plus minus signs in math? All right, who has seen minus plus signs? They work fairly the same way. The idea is when you see plus minus in one place and then you see minus plus in another, generally you have your choice in either one. Right? So here, the way we deal with it is, say, by position. If we are moving the observer towards the source, we use the top symbol. And again, if the source moves towards the observer, we use the top symbol. Right? So if we can remember that and the formula, then it makes sense. Now, you're perfectly free to make use of the other forms of, the other formulas we've seen. They're just specialized. You have to know where they apply. This formula and one rule comes up okay. Now, the other thing I'll point out about all of these formulas is you need to have an intuition of what's going on. Right? If two objects are getting closer together in principle, then it should hear a slightly higher pitch. If they're getting further apart, it should be slightly lower. But you could have examples that, right, based on this formula. Like imagine you're in a car and a cop passes you, sirens going, right? So you are driving 70 miles an hour down the interstate. So you're approaching the cop. The correction that you get for your motion means that you should hear a slightly higher pitch. Now the cop is moving faster and away from you, so their correction is larger and downwards. So the overall effect is that you get a downward shift. But the directions of those corrections, the idea is that you have to check your answers after you see it. Did I actually get what I expect? Since the cop is moving away, the siren should be lower. Did I actually calculate a lower frequency? All right, so now what we're going to do is go back, I think. Yeah, so it's written out slightly neater in terms of the book. All right, so I'm going to go back and we're going to go through these examples that we had. Source moving toward, okay. So we have a train that's moving with some speed. In general, they'll tell you what the speed of sound is, or we'll go back. In general, we'll tell you what the speed is. So, right, so we have the speed of sound is given, and we have the speed of the source. It's a horn on the train. So this is the speed of the source. And then so we know the frequency of the source. We're told basically that that's the frequency of the source. So the question is, if we're an observer standing, listening to the sound, what should we hear? So first we can look at the answers and we're going to eliminate a couple of them. The train is approaching. So any answer that has a lower frequency is out. So A is out and D is out. They're low frequencies. Now, otherwise, well, we know that the frequency has to now be 477 hertz. But we have to deduce what the wavelength of the sound we perceive is. Well, that's fairly easy. We do V is frequency times wavelength. Wavelength is 343 meters per second over 477 hertz. And then so you would pick one of these answers to be the right one. And we don't actually know what that is, so I'm going to have to calculate it. It's probably C. Yeah, it's about 0.72. So the other bit is, what if you didn't have the ability to reason out what, that two of these were wrong and the other two were the same? Then you would have to go back and calculate based on our formula. So what we would do is write out the formula. The frequency for the observer is the frequency of the source times V plus or minus V observer, V minus plus V source. Right? So we'd have that formula at hand. And now we go and we pick what's moving. The observer is not moving, so V initial is 0. The source is moving, and it's moving towards us. Towards us means we pick the top symbol. So the observed frequency is the source frequency, V over V minus Vs. And so this fraction is going to look like, we'll have 415 hertz, 343 meters per second, divided by, and then we have 343 minus 44.7, so it's about 299. Let's see what it is. 343 minus 44.7, 290. Let me do a ratio on this. No, what did you do? How did you do that? One of these days I'll learn how to do this. $298.3. And that would give you 343 divided by 298 is a number bigger than 1, so you expect a larger frequency, and that's what you would get. You would get 477. So that's what I mean by intuition, is you have to check when you put your numbers in, am I going to get a number that's larger? All right. If it's approaching, do I get a larger number? If it's retreating, do I get a smaller number? So let me pause there. How are people? Clear as mud? Good? Okay. All right, so this is actually worked out, and it's using the other forms. So there was approaching and leaving, but yeah. So if you want to do it by leaving, you would use the other formula. And what you notice is that this is going to be 1 divided by a bigger number. So the parentheses is smaller than 1. You have that your observed frequency goes down. That's what you get. All right, so it is worked out. All right, so, this is just a word problem. You hear a higher pitch than you expect. Question is, well, what's possible? All right, so higher pitch means you're getting closer to the sources. So A is no good, and D is no good. B and C are both possible. And there's no way to really distinguish that unless you can measure your motion relative to the air. So for this, it'd be B and C. All right, so do I really want to go? Yeah, I kind of do. Car moves by you. You measure a frequency coming out. This is one where you don't necessarily know what the frequency is. You just want to know the size of the shift. The ratio of what you hear, the frequency you can hear, to So from approaching to moving away. All right, so we'll write what those are. All right, that's the idea, is that when you don't know how to attack something, write what things are and see if you can see a relationship. So the frequency you can hear when approaching, and I'm going to call it approaching, is the source frequency, and then, well, you're stationary, the car is moving. So our formula would look like that. And then the away is going to be essentially the opposite formula. So if I divide those, right, if I divide them, they look like that. The source frequency drops away. That's why it doesn't matter in the problem. If you're not told what it is, it probably cancels out somewhere. And then the speed of sound cancels out here and here. They're both on top. And then we have these fractions. So when we rearrange them, we'll get V plus Vs over V minus Vs. And so we look at it, 343 plus 9 is 352 meters per second. And then 343 minus 9 is 334. And then some fraction is slightly greater than 1, which it should be. Approaching should be a bigger number, moving away is smaller. Big number divided by small number is bigger than 1. And I get like 1.05. So a lot of times you can have problems that don't have very much information in it, and you're going to have to do something like wiggle around ratios and stuff. All right. So that's the end of the slides. That's all I really wanted to do today, unless you want to know how radar guns work. I can try to explain what's going on in that, because there is kind of a thing there for okay, thank you, screen sharing is closed. All right, so let's screen share this back. Screen share screen, share projection. All right, sorry about this. This is one of those weird ones. All right, so cop car, your car. So car sends out some signal. In this case, it's light, but we're going to pretend it's sound for a moment, because it doesn't really matter that, we're going to use our formula. F observed is F source, V plus minus V observer, V minus plus V source. We're going to use our formula. But what I want to go through is just what happens. Right, the idea is that you have a source and sending wave fronts out. So first you have the radar. What do you as the driver observe? Well, it is the frequency of the radar, whatever it is, times, then we say, well, you're driving away from the cop almost always. Cop's either stationary or following you, but it's going to have this formula in there. Right. And so we'll say the cop is stationary. So we'll have the source isn't moving, so we'll have V on the bottom, and then we'll have you're moving away, so V minus the initial. But then what happens is the cop has to get the information back on the radar gun. It has to figure out how fast you're going. So as this long wavelength hits you, it reflects. And so this is really the reflected. So the observed, is the reflected frequency times, then we have this stuff in the parentheses. You're still moving away, but now you're the source and the cop is the observer. So the observer is not moving, so we have V, and the source is now V moving away is plus your speed. So note that this, we're just going to plug in this thing into this. So our actual, stop that. Our actual observed frequency looks like the source. And then we have two sets of terms. V over V plus Vs and V minus V naught over V. And then they cancel out. And the idea is that you have basically, these are the same. So this is going to be something that looks like that. Now, the point of this was not to get you to a formula to deal with reflections. The point was that you can see problems with the reflections. And so I want you to be able to manipulate it, to realize that when something reflects, then you're going to switch what is source and observed. Basically, after reflection, the thing reflecting is the observer, and then when it reflects off, now it's the source, right? Because when we say source and observer, we mean where is the sound moving from? Is it from this person to this person, or from this source to this observer? So, yeah, if you wanted to fight tickets in court, you need to make sure the cop knows how the radar works. In general, it's not worth it. Just pay the man. Y'all have any questions? All right. On Monday, we'll do the lab with different media. So it'll be like different types of springs, what happens when that changes. And on Tuesday, we'll start with temperature stuff. See y'all Monday.
Professor, can you go back to that slide, tell us when to use the plus and minus?
Yep, there we go.
So there's like the top part of the siren song going away from me, and I'm coming towards it. Then I'm getting close to it where I use the plus, but since it's going away from me, I would use the plus.
So that's the trick. When we say towards and away, what we really mean is your velocity, like pick a point in the middle, all right? And the air there is not moving. Are you moving towards that point or away from that point?
I'm moving towards it.
Right. So you would pick the top symbol.
And the source is moving away. So I would do pluses on both sides?
Yes.
Okay. That's what I thought.
Yeah. And so what it does is you get a correction for one of you moving and then a correction for the other one moving, and they partially cancel.
That makes sense.
Yeah.
Okay. I was under the impression that if one was a plus, the other had to be a minus.
No,
that makes more sense.
No. Is it in this case? You get to pick based on the physics. You don't follow any conventions in math.
That makes a lot more sense.
Well, thank you. No problem.